Hi there, Mr. Sutton here, bringing you the BC Calculus 710 Extra Practice number 5 solutions on alternating series test. For this problem, we want to know which of these is the interval of convergence for this series. Since this is not a geometric series, to find the interval of convergence, we need to use the ratio test. So I've got the limit as n approaches infinity of absolute value of n plus 1th version of this over the nth version of this. So up top I've got x plus 4 to the n plus 1 over n plus 1 in the parentheses times 5 to the n plus 2. That's my n plus 1 version of that. And now the nth term is just going to be the summand with no change downstairs. Same change flip now to get the fraction simplified a little bit. I've got x plus 4 to the n plus 1 times n times 5 to the n plus 1. That's all in my numerator. Downstairs, I've got n plus 1 times 5 to the n plus 2 times x plus 4 to the n, so a whole bunch of stuff there. I can reduce a few things. These 5s are going to reduce to leave me with just a 5 downstairs, and these x plus 4s are also going to reduce, leaving me with an x plus 4 in the numerator. So up top, I've got an n, I've got an x plus 4, and that's it. In the denominator, I have this n plus 1 still, and I've got a 5, and that's all that's down there. As n approaches infinity, I can forget about this plus 1 that's next to the n right here, because compared to n, it's growing so slowly, not at all, in fact. So I basically have x plus 4n over 5n. N's cancel, leaving me with just x plus 4 over 5. And now, in order to converge, for my series, my nth ratio that I just found here has to be less than 1. Well, let me solve for x in this situation. I can start by multiplying by 5, and I don't need to get rid of absolute value before I do that. So I have absolute value of x plus 4 less than 5. And now I'll just rewrite this without the absolute value. So I have negative 5 less than x plus 4 less than positive 5. Subtracting 4 from all three sides, we have negative 9 less than x less than 1. And that's a big question mark. Because I use the ratio test, there's some ambiguity at these endpoints. I have to actually test them to see whether or not we converge there. And I mean, if you look at the answer choices, there's actually only one answer choice with negative 9 and 1. But, you know, other questions, you might see different types of parentheses. So let's just verify that this is actually the interval of convergence. So let's test negative 9 first. If x equals negative 9, what's happening in this function here? So that's going to be negative 9 plus 4, which is negative 5. So let me just write out that stuff so far. Now, in this situation, we can kind of cancel some things out here. I can really think of this negative 5 to the n as negative 1 to the n times 5 to the n. And 5 to the n over 5 to the n plus 1, well, that reduces to just give me a 5 in the denominator. So this is really then going to be negative 1 to the n over 5n. And I could go a little bit further here if I wanted to. I could actually factor out a 1/5 from my summation so that inside I just have negative 1 to the n over n. Once I do that, I see that this is none other than the alternating harmonic series, which is known to converge. Go me. All right, so for my next trick here, we're going to plug in 1 for x. So if I plug that into the original series, well, now I just have 5 to the n over all that stuff down there. And again, the 5s can reduce so that I just have a 5 in the denominator. So this is 1 over 5n again. And just like I did up here, I'm going to factor a 1/5 out. Now I have 1 over n inside the summation. Now 1 over n is just the regular harmonic series, which is known to diverge. So at the end of the day here, we're converging at negative 9, but not 1. So my interval of convergence, my true interval, is going to be bracket negative 9, comma 1 parentheses. So including negative 9, not 1. So that does confirm answer choice A. For this problem, we want to know all p-values for which this series is going to converge. So the key on this one is recognizing that this is an alternating series. Because this alternates, as long as we can show that it is also decreasing in absolute value to 0, we will show that it converges. So a way of showing that is to take a look at the limit as n approaches infinity. So the limit as n approaches infinity of 1 over n to the p, that is going to converge if that limit goes to 0. because that would show us that we're decreasing to 0 in absolute value. Well, what values of p would make this limit come out to 0? In order for this thing to get smaller as you plug in larger and larger values of n, p needs to have a value of, well, not 0, because if this was 0, then you'd just be adding 1 a bunch of times. And p can't be negative either, because then it's actually in the numerator and this whole thing goes to infinity. So p then just must be positive, greater than 0. Any p-value bigger than 0 will cause this thing to eventually go to 0. So that means we have to pick answer choice C. For this problem, we want to know which of these conditions are necessary to conclude a series converges using the alternating series test. So the AST says a series is going to converge if the terms alternate and decrease in absolute value to 0. So terms alternating, that's what this first condition is getting at. Terms alternate in sign for all n greater than some n, some positive n. So they're basically saying that, hey, the alternating doesn't have to start immediately, but at some point this thing has to start alternating and keep alternating. Anyway, option 1 here is covered by this terms alternating piece. And now decreasing in absolute value, so that's what option 3 is all about. The a plus 1th term being less than or equal than the nth term, the n plus 1th term being less than or equal than the nth term at starting at some value for n. So that's option 3 for this decreasing in absolute value. And going to 0, that's talking about the limit as n approaches infinity being 0 as well. So this thing has to pass the nth term test. So there's option 2. So really you need all 3 of these things, choice D, in order to use the alternating series test. For this problem, we want to know which series converges conditionally. So this is a little bit tricky because it's not just about whether or not a series converges. Converging conditionally, remember, means that you converge only when you take a look at the alternating version of a series. If you could converge without the series alternating, then you converge absolutely, not conditionally. And if you diverge, then you don't converge at all, so you can't converge conditionally in that case either. So let's take a look at which of the 3 possibilities each of these series is. Taking a look at this first one, we see that if we take the limit as n approaches infinity of that nth term right there, since I have a number whose absolute value is greater than 1, and I'm multiplying it by itself over and over again, as n gets bigger, this is going to get further and further away from 0. So I guess you could say positive or negative infinity, but really it's alternating back and forth. There is no limit. So we could say, since this does not equal 0, that we're going to diverge by the nth term test. So it can't be choice A because we're diverging, not converging at all. With choice B, we have a series that is definitely decreasing in absolute value to 0 and alternating. If you consider the limit as n approaches infinity of this stuff, factorial is going to outpace exponential growth. But can this converge without the alternating piece? Well, for that we have to look at the absolute value version of this, 2 to the n minus 1 over n minus 1 factorial. And for that we're going to need the ratio test. So let me take the limit as n approaches infinity of the absolute value of n plus 1th version of this over the nth version. So up top I've got 2 to the n over n factorial divided by 2 to the n minus 1 over n minus 1 factorial. And normally I would show the step of same change flip here. I would have 2 to the n times n minus 1 factorial over n factorial times 2 to the n minus 1. But I'm kind of short on space, so I'm going to do some reducing kind of in place here without showing that step. So I'm going to end up with 2 to the n and 2 to the n minus 1 on opposite sides of the fraction. Those can reduce to give me just a 2 in the numerator. And I'm also going to end up with an n factorial downstairs and an n minus 1 factorial upstairs. Those reduce to give me just an n in the denominator. And now the limit as n approaches infinity for this thing is just going to be 0. Since 0 is less than 1, that means that this series converges absolutely by the ratio test. Because it converges absolutely, it does not converge conditionally. So we move on. On this next one, considering the absolute value version of this thing, basically 1 over radical n, this is a p-series with a p-value of 1/2. Since 1/2 is less than or equal to 1, this is going to diverge, or at least not converge absolutely, because of the p-series test. But now if we consider the alternating version of this, well, this is a series that alternates and whose terms decrease in value, absolute value, to 0. If you take the limit as n approaches infinity, this thing is still going to 0. So because our terms alternate and decrease in absolute value to 0, this converges conditionally by the alternating series test. So probably choice A is our answer, but, well, why not just look at B, or D, right? I mean, we're already there. If we look at D, so this thing also is going to converge by the alternating series test, just the alternating version of this. Now, if we look at this without the alternating, you essentially have a geometric series with 1/5 as your common ratio, or I should say a geometric series whose common ratio's absolute value is 1/5. Since the absolute value of the common ratio is less than 1, this is going to converge absolutely by the geometric series test. So this won't be the answer either, because it doesn't. Because you don't need the alternating to make this converge. So then only choice C converges conditionally. For this problem, we want to figure out the alternating series error bound if a partial sum with 3 terms is used to approximate the value of this series. So using the alternating series error bound, we know that if a series' terms are alternating and decreasing in absolute value to 0, then the error is bounded by the absolute value of the next term. So we basically just need to take the absolute value of the next term after using the first 3 terms. Well, to use the first 3 terms, we would have to plug in 3, 4, and 5 for n, which means that to get the next term, we have to plug in an n value of 6. Okay? And by the way, we don't need the -1 to the n plus 1, because this is going to be absolute value now. So plugging in 6, we just have 6 over 2 to the 6. So that's what the error is going to be less than. Of course, we might have to simplify this a little bit. So 2 to the 6 is 64. 6 over 64, if I reduce that by 2, that's going to be 3 over 32. And that is one of the answer choices, choice A. On this one, we want the interval of convergence for this series. Since this is not geometric, we use the ratio test to figure this out. So I have the limit as n approaches infinity of absolute value of n plus 1th version of this over the nth term. So that's going to be x plus 3 to the 3 parentheses n plus 1 over n plus 1 times 8 to the n plus 1. And 3 parentheses n plus 1, I'm just going to simplify that to 3n plus 3. So now we have the nth version of this, which is just the original summand down here. Same change flip, we have x plus 3 to the 3n plus 3 times n times 8 to the n. So that all ends up in my numerator. Down below I have n plus 1 times n to the n plus 1, 8 to the n plus 1 times x plus 3 to the 3n. And it's time to reduce this a little bit. These 8s can reduce to leave me an 8 in the denominator. These x plus 3's reduce. If I subtract the exponents here, I end up with an x plus 3 cubed in the numerator. So upstairs then, I've got n. This 8 to the n is gone, so we just have n and x plus 3 to the 3rd. In the denominator, I still have an n plus 1. I have an 8, and these x plus 3's are gone, so just 8 and n plus 1. As n approaches infinity, I can ignore this plus 1 next to the 8 in the denominator. So I've basically got n times all of this stuff times 8n, or divided by 8n. N's are going to cancel, leaving me with just x plus 3 cubed over 8 in my absolute value. And to converge for this series to converge, this ratio here, this nth ratio that we just found, has to be less than 1. So solving then for x in this situation, I can start by multiplying by 8 and cube rooting everything. So that gives me absolute value of x plus 3 less than 2. And now I'm going to rewrite this without absolute value. So I have negative 2 less than x plus 3 less than 2. Subtracting 3 everywhere, we have negative 5 less than x less than negative 1. And because we got this with the ratio test, we're not sure about the endpoints yet, whether or not this should be less than or equals for each of these. So we're going to have to test out negative 5 and negative 1 in the original series to see if they make the series converge or not. So if x equals negative 5, plugging that in here, that's going to be negative 5 plus 3, which is negative 2. Negative 2 basically to the third to the n. So this is negative 8 to the n. That combines with the 8 to the n down here to give us negative 1 to the n over n. So that's the real series we're looking at. And you might recognize this one. This is the alternating harmonic series, which is known to converge. So we do converge at the endpoint negative 5. How about the endpoint x equals negative 1? So at that endpoint, up here now plugging in negative 1 for x, we have 2 to the 3 to the n, so that's basically 8 to the n. Over another 8 to the n just gives us a 1. So we end up with then just 1 over n. And 1 over n, that's another infamous one. That is the harmonic series, which is known to diverge. So we converge at negative 5, but not at negative 1. My final interval of convergence then is going to be negative 5 less than or equal to x less than negative 1. And that is going to be answer choice B. On this free response problem, we have a Taylor series for f about 0, so basically Maclaurin series, given by this summation right here. Our first task is to figure out the fifth derivative of f at 0. So the key on this one is remembering that there's actually a place for the fifth derivative when you construct one of these Maclaurin series. We know that the coefficient of x to the fifth is going to be the fifth derivative of 0 over 5 factorial. So if we set this equal to the actual coefficient of x to the fifth in this series, we can use that equation to solve for the fifth derivative. Well, what is the fifth coefficient going to be, or the x to the fifth coefficient? That's going to be what I get when I plug in a value of 5 for k, because that would give me x to the fifth. So that's going to end up being 2 to the fifth over 3 times 5. And at this point, all I have to do is multiply by 5 factorial in order to get the fifth derivative of 0 by itself. So we can write 2 to the fifth times 5 factorial over 3 times 5. Since this is all constants at this point, you could actually leave it like this and just move on to the next part of the problem. That would be wise if this is the actual AP test you're doing this on. But just because we're all friends right now and this is not the actual AP test, just for fun, I'm going to simplify this. So the key to simplifying this one without a calculator is recognizing that 5 factorial is really 5 times 4 times 3 times 2 times 1. The 1 I don't have to worry about. The 5 out of that cancels with this 5, as does the 3. So really all that's left from 5 factorial, if I expand that, is a 4 and a 2. So we have 2 to the fifth, which is 32, times 4 times 2. So 32 times, let's do 32 times 2. That's pretty easy. That's 64. 64 times 4, you might remember that, being 256. But if not, well, there it is again. So this is as good as it's going to get. For this part, they want us to use the ratio test to find the interval of convergence for the Taylor series here. Well, since this is not geometric, we're going to have to use the ratio test whether they told us to or not. So we're going to have the limit then, as n approaches infinity, of the absolute value of n plus 1th version of this over the nth version. So that would be, let's see here, 2 to the k plus 1 times x to the k plus 1 over 3 parentheses k plus 1, or 3k plus 3, whether or not you want to simplify early. And then, so that was the n plus 1th version. And now the nth term is just the original summand, 2 to the k times x to the k over 3k. Same change flip, we've got 2 to the k plus 1, x to the k plus 1 times 3k in the numerator. Denominator, we've got parentheses 3k plus 3 and 2 to the k times x to the k. We can do a whole bunch of reducing here. These 2's can reduce to just a 2 in the numerator. Same thing with these x's, just an x in the numerator. So we have a 3k and a 2x upstairs. Downstairs we just have the 3k plus 3 because everything else got wiped away by reducing. As k approaches infinity, we can forget about this plus 3 in the denominator. So we really just have 3k 2x over 3k. The 3k's cancel, leaving us with just the absolute value of 2x. Now to converge, the nth ratio, this thing right here, must be less than 1. So let's just go ahead and solve that for x. So if we divide both sides by 2 here, we have absolute value of x less than 1/2. And then, since I want the interval of convergence, I'm going to rewrite this without the absolute value. So negative 1/2 less than x less than 1/2. But that's not the end of the story. That's why I have a question mark here. Because we found this using the ratio test, we don't know about the endpoints yet until we actually plug them in to see if the endpoints make the series converge. So let's say that x equals negative 1/2. Plugging that in, I've basically got negative 1 over 2 to the k. These 2 to the k's cancel, but you still have a negative 1 to the k upstairs. Now, to get to the bottom of the convergence for this, a little trick you can use here, you can basically factor a 1/3 out of the summation, like so. And then inside, you just have negative 1 to the k over k, which we recognize is the alternating harmonic series. And we know that that one converges without doing any further proof. Now let's say that x equals positive 1/2. Well, in that case, you basically have 1 over 2 to the k, which is going to cancel with this 2 to the k, leaving us just 1 over 3k. We can use the same trick here that we did up here, just pulling a 1/3 out of the summation. That'll leave us with just 1 over k inside. And inside here, we recognize that we have the harmonic series, which we know diverges. So at the end of the day here, we are converging at negative 1/2, but not 1/2. So then our final interval of convergence will be negative 1/2 less than or equal to x less than 1/2. For this part, they want us to use the second degree Taylor polynomial for f about 0 to approximate f of 1/4. So it might be helpful to write out the second degree Taylor polynomial before we try to use it to approximate anything. To get the second degree polynomial, I have to plug up to k equals 2 into this formula here. And they told us we have to start with k equals 1. So let's do that. That'll be 2 to the 1 over 3 times 1 times x to the 1. And this is just giving us, I'm going to call this T2, second degree Taylor polynomial. Now for so that was the first term. For the next term, we have 2 to the second over 3 times 2 times x to the second. And since we've made it up to the second power, we've got our second degree Taylor polynomial. So just simplifying this a little bit before I plug in, this is 2/3 x plus, well, let's see here, this would be 4 over 6, which I can reduce to 2/3 x squared. Next, let me plug in 1/4. So I'm going to write f of 1/4 is approximately equal to all of this stuff with 1/4 plugged in for x. And I can actually stop here since this is numerically equivalent to whatever the answer is. Again, note that I wrote approximately equals. If I just wrote equals, then I would not get the point. But if you wanted to simplify this, let's see what that would come out to. So this would be, let's see here, 2 over 12, which is 1 over 6. And for this next one, this would be 2/3 times 1 over 16. So that would be, let's see, 2 over 48, which is 1 over 24. Well, this is really 4 over 24 plus 1 over 24. So 5 over 24 would be our final answer on this one. For the last part of this problem, we're given that the absolute value of the third derivative of x is less than or equal to 128 over 3 on the interval from negative 1/4 to 1/4. And they want us to use the Lagrange error bound to show the approximation from part C differs from f of 1/4 by at most 1/9. So we're talking Lagrange error bound. We basically want to show that if I do the Lagrange dance, I get an error that is at most 1/9. So I'm going to say that my error is going to be less than or equal to the following, and now I have a big fraction. Up here I have the max derivative, and let's see here. Which derivative do I need? Well, let me figure out what interval I'm taking the max over to start with. So this is going to be the max derivative on the interval between the launching off value, the point of tangency, the center, and whatever value I'm trying to approximate, which is x equals 1/4 in this case. So I'm going to need the max derivative on the interval from 0 to 1/4 of, and now which derivative do I need? So because I used my approximation in part C with a second degree Taylor polynomial, that means that everything in this Lagrange formula needs to be third. So we need the third derivative, absolute value of that. I need third factorial, and I need x to the third. Specifically, I need 1/4 to the third power. All right, well, let's plug in a few things here. So the good news on this is they're not making us work very hard for this max derivative. They told us that the third derivative absolute value is less than or equal to 128 over 3. So 128 over 3 is the max of that third derivative absolute value. So I'm going to write 128 over 3 up there. That's the only change from here down to here. And now I need to clean this up a little bit. Normally you wouldn't need to simplify, but I need to show that this is less than or equal to 1/9. So let me go ahead and clean it up. I've got a 128 in the numerator. This 3 under the 128 can move down to the denominator to be with the 3 factorial. And 3 factorial is really just 6. And this 4 to the third can also stay in the denominator. That's really 64. So I have 128 over 3 times 6 times 64. Well, 128 over 64 reduces to 2. So we have 2 over 3 times 6. And 3 times 6 is 18. So 2 over 18 is going to reduce to 1/9. And since we've shown that error is less than or equal then to 1/9, we've done what they asked.